All right. So hello, everyone. We're very pleased to host Professor Daniel Lecoanet from Northwestern University, specifically CITA. So Daniel Lecoanet is an expert in numerical hydrodynamics and different fluid dynamical processes. In particular, he's worked a lot on convection and radiation zones within massive stars. So he got his PhD at Berkeley with Elliott Quattert and went on to a postdoc at both the Lyman Spitzer Junior Fellow as well as Princeton Center for Theoretical Sciences Fellow. Now he has a very big group already, although he just started at Sierra, working on a lot of very interesting problems. And in particular, which I'm sure we're also going to hear about, he's developed a beautiful code, a pseudospectral code known as Dipole, that can solve basically any sort of fluid dynamical problem that you want, and it's very, very easy to use. And so thanks again for coming here, and we're all looking very much forward to your talk.
Great, thank you very much for the invitation. I guess the first thing that I wanted to do is actually not on my slides. I just looked this up. So I found on your website, there's this presentation archive, and a little over 10 years ago, I gave a talk here on Rayleigh Taylor instabilities in a dilute plasma. And I remember this, I think this is the first scientific talk I ever gave. I was here, and if I remember correctly, my laptop died halfway through. So I'm just hoping that won't happen again today. We'll find out. Okay, so today, in the intervening 10 years, I've moved on from Rayleigh Taylor instability, but still thinking a bit about magnetic fields. So if you look up at the sky, mostly what you'll see is stars, okay? Some image, and when you see stars, there's kind of a few things that you might notice. One is that they have different colors. So you might have stars that are a bit redder, some that are a bit bluer. Okay? And then the other thing is that they're of different brightness. Okay? And to lowest order, I mean, this is basically the only information that we have about stars. Okay? And by itself, it seems like it's just two data points. So can you really do very much with 2 data points? Well, you can't. So kind of the game has been to try to disentangle these 2 things and get richer data from them. So kind of traditionally, the way that you did this was instead of just calling this like red and blue, is instead looking at the spectral information of the light. So in terms of the frequency of the light that you see, which I'm denoting here as nu, opposed to in the future I'll be talking about f as a time frequency. So for instance, this is some star. You can get the flux as a function of wavelength. Does anyone have any guess of what kind of star this is? Anyone know? No. Okay. This is a BE star. Okay. I think these are silken lines. Okay, so this is this is kind of traditionally how people got more information about stars, that they looked at the spectral characteristics, and you can get lots of information about what's going on from that. But a new way is, and I guess this isn't not really new because we've known about variable stars for a very long time, but now we can study variable stars with much more precision than before. So the brightness of a star is changing in time. So here I'm plotting the flux coming from a B star as well as a function of time, and you can see that there's all these oscillations. Okay, and the way that I think about this is that this sort of spectral information is giving you information about what's going on at the surface of the star. Which of course is very useful, and you can try to understand what's going on within a star by asking what types of things would be happening at the surface of different types of stars, try to get information that way. However, these types of information, when we're looking at the brightness of the star as a function of time, that's telling you about the waves that are propagating within the star. So this is kind of a much more direct measurement of what's going on inside the star. And understanding the properties of these waves is called astroseismology. And this has, I think, really revolutionized our knowledge of stars. Okay, and this is only possible because of these space satellites like TESS, or before that, Corot, Kepler. In the future, we'll have Plato. And the way that I think about these is that somehow stellar astrophysicists convinced everyone to get excited about these exoplanet things, which I think are kind of boring. But we kind of like duped everyone into constructing these really great missions for studying stars by telling them that they learned something about exoplanets. So yeah, that's right. Yeah. So this is a great benefit to people studying stars, of course. Okay, so now why do we care about stars? I mean, I think stars are interesting in and of themselves, but maybe you guys think stars are as boring as I think exoplanets are. So I mean, so what's interesting? Like how do stars connect with other parts of astrophysics? Well, of course, exoplanets are normally orbiting around stars. These are the progenitors of transients and compact objects, including binary systems, then lead to black holes. They also give chemical enrichment in galaxies and are an important part of the evolution of galaxies. So these are these are kind of a few different places where stars are important, broader in astrophysics, but then there's a bunch of existing problems in stellar astrophysics which are actually important for all these applications. So for instance, a big question is how is angular momentum transported within stars? It's not really understood so well how this works. I mean, that's important if you want to know what's the initial spin of a neutron star, or what sets the spin of black holes. We're starting to probe with LIGO and Virgo. If stars start spinning a lot, it seems like they're good at giant magnetic fields, and that could have implications for habitability of exoplanets. Another important problem is transport of energy. So this is normally parameterized in stellar astrophysics with the mixing length parameter. So we don't really understand how convection can transport energy in regimes where it's not very efficient, which is often the case at the surface of stars. And this is actually really important for exoplanet observations, because oftentimes the largest uncertainty in the size of exoplanets doesn't come from anything associated with the observation of the exoplanet. It's an uncertainty in the star itself, that we don't really know what the size of stars are intrinsically. We have some models, but there's large uncertainties in part because of this unknown process of energy transport, which is parameterized with a mixing length parameter. Another major problem in stellar astrophysics is binary interactions. So almost every massive star is born in a binary. So sometimes even higher order systems like triples. And oftentimes over the course of the lives of these stars, they interact with the other star in the binary if they're close enough. And of course, this is very important for getting compact objects which might merge in the lifetime of the universe. But then it also really influences the evolution of the star. That leads to stars which have different chemical compositions, when they explode as a supernova, what kinds of elements are they going to release into the universe? Another really important problem in stellar astrophysics is mass loss. So it's known that especially massive stars, they're so luminous that they're able to eject material off their surface. And actually, for very massive stars, the mass of the star can change by an enormous amount. I mean, maybe even like a factor of 2 over the course of its life, or even as a main sequence star, there can be substantial mass loss. This is a big uncertainty. People don't understand all the processes that are involved here, but it's very important for setting the masses of compact objects. It's important for properties of transients, especially if you have a supernova that goes off. It's going to propagate out into all the material that the star emitted before it died. So that can have some observational implications. And also, kind of the mass of a star plays an important role in determining how much material gets fused together and what the final chemical state of the star is. The last one that I want to mention is chemical transport. And a big question here is what's happening at the interface between convection zones and radiative zones in stars. So convection is a very efficient mixing process. So it's thought that in a convection zone, that material is relatively homogeneous. Whereas in the radiative zone of the star, you have very little radial mixing, at least, because you're stably stratified. There's an enormous potential energy cost to any radial motions. However, at the interface between the two, it's kind of unclear what happens to the chemicals. And this can play a really important role in the evolution of massive stars. The main sequence lifetime of a massive star could change by as much as a factor of 2, based on how much chemical mixing you have at the boundary between the radiative zone and the convection zone. If you're able to mix in fresh hydrogen from the radiative zone into the convection zone, that's more fuel that can let the star live longer. So these are all a bunch of I would say that, at least in my opinion, these are some of the major outstanding problems in stellar astrophysics that people are trying to track down, and in particular, these questions of angular momentum transport and chemical transport have gotten a lot of new data from astroseismology. So I just want to delve into those 2 points in a little bit more detail. So first, I'll start with the angular momentum transport. Okay, so I'm going to show you this this plot here. It's going to show the period of the rotational period of the core of an RGB star. These stars have a mass of 1.5 solar masses, and these stars at the terminal age main sequence, they start off at this radius. And then as the stars evolve up the RGB, the radius increases, so they kind of move towards the right. Okay. So first I'm going to show you some theoretical models, and then I'll show you what the data are from astroseismology. So the first thing that you could do is that you might imagine that you have a star just initially rotating as a solid body at the surface. I think this is the rotational velocity of 50 kilometers per second. And then you just imagine that the star evolves, conserving angular momentum. Okay, and what you find is that the period of the rotational period of the core goes down. That's because the material is shrinking. It's like the ice skater that's pulling in their arms. They start to rotate more quickly. You have a lower period. Okay, So this is a theoretical model assuming angular momentum conservation. Okay, and now these are a bunch of other models with various other assumptions. So like Taylor screw dynamo here. I think that you're just assuming that that you kind of maintain some surface period. Okay, and then you can look at the observations. So the way that these observations come about is that you see these oscillation modes, these coherent oscillation modes at the surface of the star, and they have a rotational splitting. Okay, so to leading order, modes that are propagating prograde and retrograde relative to the rotation would have the same oscillation frequency, but there's a perturbation that shifts the frequency of the wave slightly based off the rotation rate. Okay, so from that rotational splitting, you can measure what the rotation rate is of the cores of these stars, and you can see that it lies nowhere near any of the theoretical predictions. Okay, now before these measurements were made, I think that people probably thought that that at least some of these theories would be kind of close to being true, and then it turns out that that actually we have no theory that works. Okay? So this is kind of like one of the big questions. No one understands what is causing these types of rotation rates in the cores of these stars. Okay, so a big open question that has come from astroseismology. Okay, now the second thing that I want to talk about is chemical transport. So we're going to be looking at now solely pulsating B stars. These are massive stars, a few times more massive than the sun. They have a convective core and a stably stratified radiative envelope. Okay, and something that you might wonder is what's the mixing that's occurring at the interface between the convection and the radiative zone. Okay, again, if you have mixing there, you can bring in fresh hydrogen fuel into the convection zone and extend the life of the star, maybe by as much as a factor of 2. So if you actually look at some of these stars, so this is 6 examples from a recent paper by Pedersen, you see that the brightness of the star is oscillating with time. And if you take a Fourier transform of this, in time, you get all these oscillation modes. Okay, so this is kind of like the main data output of these astroseismic measurements that we see these oscillation modes here. Okay, and these are all G modes. So the restoring force is gravity, and one of the main characteristics of G modes is that the period between two similar G modes is normally the period spacing between them is normally about constant. Okay, so what people often do is instead of plotting the frequency or the period of the wave, they'll plot what is the period difference between two associated waves. So that's that's what they've done on this plot here. So basically from this diagram, you identify all the frequencies. Okay, you pick which modes you think are associated with each other, and then you plot the difference between the periods of those modes. So that's what you have for the 6 different stars, and you can see that sometimes it's about flat, like in this case. Or sometimes there's kind of more secular trends, okay? And then there's like all these bumps as well. In this diagram, the actual data are the diamonds, and then the kind of like lighter circles, those are their best fit models, okay? So what do these different trends mean? Well, it turns out that if you have kind of this secular trend like this, that's actually related to the rotation in the star. Okay, and then these dips, those have to do with the chemical gradients. Okay, the the envelope of the star is all hydrogen, basically, whereas the core is a mix of hydrogen and helium. So you have a chemical gradient where you go from having quite a bit of helium to no helium. And that chemical gradient is what produces these dips. Okay? And the properties of those dips can then be used to try to figure out the chemical transport that has occurred in these stars. So in this paper, what they did was that they tried a bunch of different models for what the chemical transport is. So they parameterized this in terms of mixing diffusivity. And what they found is that basically it's these parameters here, these ones do the best. In particular, this size 7. So this is saying that it seems like that there's a region outside the core of the star where there's kind of a pretty constant level of high diffusivity, and then it seems like it falls off very abruptly, and then there's something else going on outside of that. That seems to match the observations quite a bit better than when the mixing kind of falls off gradually. Okay, so what does this mean? We still don't exactly know, but at least this is giving us some really in-depth information about chemical transport in these stars. Okay, so this is just kind of some of the recent things that people have been thinking about in stellar astrophysics. But there's one big thing that I left off, which is magnetic fields. Okay, so as we all know, if you want to make something more complicated in astrophysics, you just put in some magnetic fields. But magnetic fields are actually really important for many of these processes. For instance, with angular momentum transport, if you have a radial magnetic field, that can lead to a lot of angular momentum transport. In fact, one of the models that I showed on that plot, the Taylor-Sprout model, is an angular momentum transport mechanism that's done entirely by magnetic fields. It's thought that the rotation rate in the radiative core of the sun is about constant due to a magnetic field there. Okay. Mass loss, for instance, mass loss is strongly tied to magnetic fields as well. You have there's like an alphane point, which tells you how things are moving away as you eject them from a star. Okay, and so what I want to do in the rest of this talk is talk about a couple of cases where we think magnetic fields might be able to understand some observations of stars. Okay, so first I'm going to talk about red giant branch stars, and then I'll talk about a specific B star that we looked at recently. Okay, so these are some astroseismic measurements of a few red giant branch stars. So you measure the brightness as a function of time, you take the Fourier transform, you get a bunch of peaks. Okay. Now the key thing here is that they've done some sophisticated analysis to determine what types of oscillation modes you're getting. Okay. They've labeled them with L, the spherical harmonic degree. You can think about these. The angular structure is well described by spherical harmonics. L equals 0, that's spherically symmetric. L equals 1 is dipole mode. L equals 2 quadrupole, etc. So they've done this analysis, and they think that they know what are the spherical harmonic degrees associated with the different peaks. Okay. And in each of these pairs, if you look at the L equals 0 mode, those are the spherically symmetric oscillations. Both the amplitude and the frequencies are very similar between these two stars. Okay, same for each pair. But the difference is that at the top, you can see that the L equals 1 oscillations are of similar magnitude to L equals 0, whereas here they're much lower. Here, you barely see them at all, and that's the same thing here as well. Okay. The fact that the L equals 0 are very similar tells you that these two stars should be virtually identical. So then the question is, what's the difference between them? that gives you a strong L equals 1 here or here, but almost no L equals 1 here or here. Okay. And our guess is that this has to do with magnetic fields. Okay, why is that? Well, there's an intriguing fact, which is that the percentage of stars that have these depressed dipole modes, the small L equals 1 modes, there's a strong mass trend. Okay, low mass stars, you hardly see these depressed modes at all. Whereas higher mass stars, it becomes very prevalent. Sometimes maybe even greater than 50%. Okay, and it seems like this turns on at a mass of, I don't know, kind of around like a 1.2 or so, which intriguingly is about the mass where you transition from having a stably stratified irradiative core in the center of a star versus for higher mass stars you have a convective core. Okay, so kind of there's a hypothesis. I mean, this was work led by Dennis Stello and also Jim Fuller, that they thought that maybe what's going on is that these higher mass stars, when they were on the main sequence, they had convective cores. They had the convection was able to generate a large scale magnetic field. And then when the star becomes a red giant branch star, then it's you end up with a radiative core, but the waves are somehow interacting with that magnetic field. Whereas for a lower mass star, it never had a strong core magnetic field to begin with, so that never happens. Okay, so we want to try to understand this a bit. So first, I'm going to tell you about G modes. So those are kind of the characteristic of these modes that we're seeing. I want to think about them in a very specific way. So to simplify things, I'm not going to use spherical geometry. I'm just going to consider a box. So box has a horizontal size Lx and vertical size Lz. I'm going to assume that there's gravity downwards, and that we're in a radius zone. So the way that I want to think about that, so you can imagine that you kind of have like high density down here and low density here. Okay. Now, of course, in a star, what's relevant is the entropy, not the density. But just to try to simplify things here, I'm just going to talk about things in terms of the density. So you can write down the equations of motion, which looks something like this. So you have a momentum equation, the pressure gradient, and gravitational acceleration. We're going to assume that the fluid is locally incompressible. And then you have an advection equation for the density perturbation, which is related to the Brunt-Väisälä frequency, n. Okay, and so physically speaking, what these G modes consist of is that you imagine that you have this low density here, high density here. You take a fluid parcel in the middle, which has intermediate density. If you perturb it downwards, it's lighter than its surroundings, which is at high density. So there's a buoyancy force upwards, so it'll rise up, overshoot its original position, and then end up too high. Now, since it's at intermediate density, it's heavier than its surroundings. So the buoyancy force downwards, so it'll fall and undergo oscillations. So the restoring force is gravity. That's why we call it a G mode. Okay, so these are the equations which describe that process. And what we're going to do is that we're going to imagine that you have an oscillation at a given frequency. Okay, so the frequency is omega. And then we're going to take a WKB approximation. So things like gravity, the Brunt-Väisälä frequency, et cetera, those in general will be a function of height, or in a star, will be a function of radius. Okay, but oftentimes these modes, they're oscillating on very small vertical length scales. So because of that, we can make a WKB approximation where we can replace vertical derivatives with an IKZ. So this is like the local vertical wave number. Okay, now if you do that and you can turn these 4 equations here, these equations here, into a matrix system that looks like this. Okay, so for instance, the first one is the x component of the momentum equation. So that's rho naught times dt of ux. So that's the x component of the velocity. If you take the time derivative, that pulls out a negative I omega. So you get a negative I omega rho naught acting on ux. Then you have a derivative of the pressure. So you have a dx acting on p prime. And then, well, there's no gravity in the x direction. So that's it. Okay, so that's the first equation. You can do that for the rest. Okay, so now this is some matrix, right? Or at least it's a linear operator. And when someone gives you a linear operator, the first thing you should always do is try to calculate the eigenvalues. Okay. So I guess I want to think of this as an eigenvalue problem, okay? Where the eigenvalue is the kz. Okay. I want to figure out what is the local vertical wavelength. Okay. And then the eigenvector is the x dependence of all these terms here. Okay. So at this stage, I have not said anything about what the x dependence is. I still have these x derivatives. A priori, you don't know what it is. Okay. But this is an eigenvalue problem, and you can try to solve for what are the eigenvalues, what are the values of kz, and also what's the eigenvector, what's the x dependence of all these variables. Okay. Now, in this case, it turns out that's pretty simple. The x dependence is, well, if you assume that it's periodic, the x dependence is that each of these things goes like ETI kx times x. The periodicity constraint says that kx is an integer multiple of pi over Lx. And if you put that in and solve the eigenvalue problem, you get this equation for kz as a function of kx and omega and n. Okay, so this is what we call the dispersion relation for these G modes, and this tells you what the local vertical wave number is. Now, the way that I want to think about this is imagine you have a wave which is probably downwards. Okay, you could ask yourself, what does that wave look like in terms of its vertical wave number, in terms of kz? Well, the funny thing about gravity waves is that it turns out that the wave which is propagating downwards has a positive kz. Okay. Normally, something that's going upwards has a positive kz, but here it's backwards. So these gravity waves are very funny like that. And a wave will propagate downwards at a speed related to what kz is. And it'll keep on going until either two things happen. The first thing is that it could either hit the bottom. The other thing is that the n squared could go to 0. Or I guess in general, kz could go to 0. And when that happens, the wave actually reflects up. And then you get an upward going wave. The upward going wave has a negative value of kz. Okay. So that's what happens for G modes. Okay. So now I want to look at what happens when you put in a magnetic field, and I'm going to do the same sort of analysis. Okay. So what I'm doing here is that I'm just imagining that you're threading a uniform magnetic field, vertical magnetic field, through this box. Okay, these are the equations that you solve. So you add in a Lorentz term, Lorentz force. And then we're also solving an induction equation for the magnetic field perturbation B prime. Okay, so if you, and then something else that's important is that we're going to assume that the Brunt-Väisälä frequency is a function of height. Okay. So now this is something that you can solve numerically. So that's what I'm going to show here. This is a simulation with the Daedalus code that that JJ mentioned earlier. So in this simulation, I'm going to drive waves at a specific frequency up here. And that's going to make waves which go upwards and waves which go downwards. I don't care about the waves going upwards, so I put a little damping layer there so you don't have to worry about them. And we'll just watch the waves go downwards. Okay, so these are the gravity waves, the G modes, which are propagating downwards. The framework here is in gray, so so I don't know if you can tell, but at least if you look, say like on my laptop, you'd notice that it kind of looks like the waves are actually propagating upwards here. They're not. That's when waves go downwards, they have a positive kz, which means that it kind of looks like they're going upwards, but they're really going downwards. However, when the waves propagate downwards, you can see they don't make it to the bottom of the box. Instead, they kind of reflect at a special height. And then you end up with waves which are propagating upwards. Okay, it produces this beating pattern. Okay, so how do we understand this? Well, again, we can do an eigenvalue problem. The eigenvalue problem is similar to what we had before, in the sense that because there's no horizontal dependence, you can decompose it into Fourier modes. The x direction, so you have a kx. Yes.
So what does the Bront-Weissel frequency look like for these simulations? I'm guessing it's a uniform magnetic field in the background, but what about the Bront-Weissel frequency?
Yeah, I think that here I'm well, you can see that the wavelength is the vertical wavelength, the vertical wave number is getting larger as it propagates downwards. So that's telling you that the Bront-Weissel frequency is increasing with depth. Okay. So these waves propagate downwards, and they're following this this relationship between kz, kx, and omega and n. This is a quadratic in kz squared. So something interesting happens when the discriminant of that quadratic is equal to 0, which is at this this height here, okay, this value of z, which corresponds exactly to where the waves reflect. Okay. So so if you plot the roots of this, you get a pattern which looks kind of like this. That you have above the turning point, you have 4 modes, which are oscillatory. You have 2 modes here, which have smaller values of kz in magnitude, and then 2 modes with larger values of kz. Okay, the smaller ones are the G modes, the internal gravity waves, whereas the larger ones are slow magnetosonic waves. Okay, so they're a magnetic wave. Below the turning point, you have 4 evanescent waves. Okay. So what's happening is that the wave propagates downwards as an internal gravity wave. And then even though its wave number never goes to 0, it actually converts at this height into a magnetic wave, which goes upwards. Okay. And that's what's happening here. So you have a wave which is going downwards. That's a gravity wave. And then what comes back up is a magnetic wave. Yeah.
What are the boundary conditions at z equals 0?
I don't remember, but it doesn't matter because waves don't go down there. I actually think the simulation is periodic. But yeah, we did different boundary conditions. It didn't make any difference. Any other questions about this? Okay, so now you can compare. Yes.
Quick question on so you got a driver.
Yep. At a given frequency.
But if we are in the interior of a star, phonons are equilibrium with the material. So there's this phonon bath. The interesting question is there a G mode bath that's basically excited, or is that irrelevant?
So in these stars, the waves are being excited by convection.
Yeah.
And you're right that I guess, so I call them pressure wave modes. set of
Yes.
phonons, but
Yeah, that's the
yeah,
issue.
the
Speed of sound with G, it's like, what's the speed? But
yes. So this is an interesting thing that for okay. So the sound waves are thought to be in like in an equilibrium.
Yeah.
The sound waves are both being excited and damped within the convection zone.
yeah,
These waves here are excited in the convection zone, but they're damped outside the convection zone.
right, yes, so they,
They're
so
actually in
the
equilibrium.
mediation layer between the convective region and the
Yeah.
and the radiative zone.
So
Is there an interesting characteristic scale for that mediation layer?
So I guess here, what I'm assuming is that I'm just assuming that the convection is leading to some G modes, which are propagated inwards. And I'm not worried about how they're being generated at this stage here.
Right.
Yeah.
Yeah, so the sourcing is not part of it. You're assuming a source to drive
right.
linear equation.
Yeah.
Yeah.
Right.
But there is feedback, which is actually how they actually.
Yeah. So of course, in real life there's feedback, but as you'll see in a moment, there maybe the sense of feedback is it's just like an energy loss from the convection.
Yeah, but it's interesting. Well, we can talk about this later.
So yeah, so I just want to say that you can compare the simulation to a WKB calculation, and they match up very nicely. Okay, but then kind of the question is, let's see, is this still working? Yeah, there we go. Okay. So then the question is what actually happens to that magnetic wave which propagates up? Okay. So to address that, what I'm going to do is instead of taking a constant magnetic field, I'm going to have a magnetic field which is very sinusoidally in the x direction, and which decays exponentially with height. So this is a magnetic field profile which has no current. Okay, so I'm going to draw this in the same way as before, or set up the simulation in the same way as before. So you drive a bunch of waves here, they propagate downwards, and then you can see that you start to develop some kind of funny behavior here. Okay, in particular, there's some stuff down here, there's some stuff up here. Again, the waves don't make it all the way down to the bottom of the domain. So in this case, the problem is quite a bit more complicated. So you have to make a bunch of assumptions about the size of various terms. But if you do that to leading order, you're left with this equation here for, and this is an eigenvalue problem. Okay, so this is a second order ODE in x, right? So you see the second derivative here. This cosine squared of x, which comes from the x dependence of the magnetic field. And this equation has an eigenvalue, which is kz. So you can figure out what are the kz's which give you a solution to this equation, which is periodic in x. Okay. So another quiz. Does anyone know what the solutions M are here of this equation? Look familiar to anyone?
Is it just sines and cosines again?
Excuse me? Very good. Yes. So this can be rewritten into the Mathieu equation, and then the solutions are Mathieu functions, which is why I called it M. So those are the eigenfunctions, and then the eigenvalues, the kz's, are related to the Mathieu characteristic functions, and you can solve for what those are. And basically, what it tells you is that as before, you have these low kz gravity waves, which propagate downwards. And then there's a critical turning point where they turn into magnetic waves, which go upwards. But then those magnetic waves actually, their vertical wave number diverges at a finite height. Okay, and that's so the turning point, the lower turning, and then there's actually there's two branches, because it depends if the gravity wave is in phase with the magnetic field or out of phase with the magnetic field. Okay, so it's kind of two different possibilities.
Basically, VA is going to 0.
VA decreases with height exponentially.
So that means that K has to go infinity to maintain the
So you would think that the KZ would increase exponentially. It doesn't increase exponentially, it diverges. So faster than exponentially. So it's not what you would have expected. Okay, so it increases faster than you would have expected. So so this is kind of what you get from the theory, and you can compare the theory to the simulations, and it seems to work pretty well, except that there's kind of some mysterious behavior that's occurring right at that special height where the vertical wave number is supposed to go to infinity. Of course, you can't do that in a simulation, so you have to be a bit careful there. Yes, that's right. Yeah. So here, in this case, we don't get phase mixing in this picture here. So the picture is, so what's the picture? So remember, we're trying to distinguish these waves with, or these stars with normal L equals 1 from these with suppressed L equals 1. And the idea is that if the core of the star has a weak magnetic field, you have a downward going internal gravity wave, it bounces off at r equals 0, propagates to the surface, and you set up a mode. Okay, that's these ones here. Okay, if there was a strong magnetic field, downward gravity wave converts into a magnetic wave going upwards. As the magnetic field drops, you go to high kz, the wave damps, and you don't see it. Okay, so this is the sense in which I'm saying that you can maybe think of this as just damping energy out of the convection zone, because the convection is exciting the G modes, which turn into magnetic waves, and then they just damp. Okay, so then these ones, those are stars with weak magnetic fields. These are stars where we think we have strong magnetic fields. Yeah.
What process damps the magnetic fields?
It would the magnetic waves are being damped normally by thermal diffusion. So when you go to the small length scales, you have thermal, rate of diffusion. So these ones have strong core magnetic fields. Okay, so as usual, I've kind of meandered a little bit too much. So I want to talk a little bit about B stars. I only have 10 minutes left. I'll try to. It's not as extensive this, so maybe I'll try to go through that.
So you can go another 5
Yeah.
minutes.
Okay. So here's a specific star. It's a pulsating B star. If you look at the brightness of the star as a function of time, you get all these oscillations. And something that's kind of strange about this star is that it has a strong surface magnetic field. Okay. So if you look at the oscillation modes, this is what the spectrum of the oscillation frequencies are, and all these red lines here, those are where they have identified the presence of a mode. There's 35 modes, of which 16 have been identified as G modes. Okay, and in addition to this star having an unusually strong surface magnetic field, another strange property is that normally stars like this have lots of low frequency modes, but this one only has a couple. Okay. So, this is what the astroseismic modeling of the star looks like. If you remember, we like to plot the period difference between adjacent modes as a function of the period, kind of like a PP dot plot or something, right? So in this case, those 16 G modes are given by the vertical lines. And then they tried to come up with a stellar structure which matches those as best as possible, and that's given by the red points here. Okay, so you're supposed to have red points every time you have a vertical line. Okay, now sometimes you have a red point with no vertical line, but it's not entirely clear why that is, but this is what they found. Okay. You can see again these characteristic dips. That's because you have a chemical gradient outside the core of the star. Okay, so so if you plot kind of the characteristics of the various frequencies associated with this star, in blue, we show the Brunt-Väisälä frequency. There's this big spike here. That's due to that chemical gradient, which is probed by these dips here, here, and here. Okay. The lowest frequency wave is given by this green line right here. Okay, and again, normally stars like this have lots of low frequency modes, which would be high period. Okay, but none are observed in this star. The question is, why not? Maybe this has something to do with the fact that it has a strong surface magnetic field. Okay, so already we have a hint, maybe related to magnetic fields. Okay, we're going to do the same approach as before. We're going to do an eigenvalue problem to figure out what the radial wave number is. Except now we're going to use a spherical geometry. Okay, we put in rotation. We're using the traditional approximation, and we just turn this into a matrix and solve for the eigenvalues. Okay, again, the eigenvalues are the KR. Okay, so if you do that, you get the following types of solutions. Okay, so this is a frequency that's actually observed in the star. Okay, this wave, you have a wave which is propagating inwards, and then you can see it might be a little bit hard to see, but right over here, right near the core, the wavelength gets really small. That's because you're in that chemical gradient region. Okay? The Brunt-Väisälä frequency becomes large. You go to very large wave numbers. Okay. In this model, I've included a dipole magnetic field. Okay. But in this case, for this frequency, the wave propagates inwards, bounces off the convective core, and then goes outwards, and can set up a G mode. Okay. So we think that this matches with the observed G mode of the star. You can plot the radial wave number as a function of radius, and you can see again that it goes up to be really large in that region where you have the chemical gradient. At higher frequencies, you end up with a bunch of alphane waves. Turns out that these are alphane resonance modes. Okay, now if you shift the frequency just slightly downwards, then the wave number of the internal gravity waves goes up, and it hits into these magnetic waves. So what happens then? Okay, as the wave propagates inwards, it looks very similar to before. Okay, but then when it hits these magnetic waves, we think what happens is that it's going to propagate outwards as one of these alphane resonance modes. And here, I think that you're going to get a lot of phase mixing. Okay, so this is the place where maybe the magnetic greenhouse effect might be a good way to think about things. Okay, so in this case, this was assuming that you had a magnetic field of about 500 kilogauss. Okay, so the idea here is that this is kind of like the lowest frequency mode that was seen. Normally, you would expect to also see this mode. Okay, so what we're doing is that we're inferring that our explanation of the fact that you don't see this mode is that we think that there might be a 500 kilogauss field in this near core region of the star, which prevents this wave from bouncing back up the lower frequency.
The surface field is weaker than that, right?
The surface field is about 1 kilogauss. I'll get back to that in a second. Okay. So now, how do you get that 500 kilogauss field in the near core region? Well, I think that there's kind of like two ideas. One is that the convective core itself generates a magnetic field. So maybe that's what we're seeing. Some of that magnetic field can leak into the radiative zone, into that chemical gradient region. If you just do kind of like a naive simulation of core convection for B star, not this specific B star, but just kind of like a normal B star, you can get magnetic fields that are the correct order of magnitude. Okay. Now, how about the surface field? Okay. Another possibility is that maybe this is what we're seeing as some surface field. As I said, at the surface, the field strength is 1 kilogauss. Okay. If you assume that the magnetic field has like a dipole sort of variation with radius, which I mean, there's not really any good reason for assuming that, other than it's like the simplest thing you could think of. Then the strength will be very like 1/r cubed. And if you extrapolate that down from 1 kilogauss to the at the surface down to the near core region, you again get about 200 kilogauss. Okay, so it seems like in this case you could get like both of these are, I would say, are in the correct ballpark. Okay? So I wouldn't say that we favor one versus the other. Okay, so I've exactly run out of time. So I just to summarize briefly, astrocosmology has lots of waves and stars. Sometimes these waves are affected by magnetic fields. You can try to understand how the magnetic fields affect waves by studying these eigenvalue problems, and that we're really only at the beginning of trying to probe magnetic field using these waves, using astroseismology. I think that there's lots more to come. So thank you.
Thank you very much, Daniel, for a wonderful talk. So we have a bit of time for questions. I'll ask the online participants if they have questions first. Oh, okay. So there, let's see here. So Arya has a question. Go for it, Arya.
Hi, that was a great talk. Thank you. My question is more about sort of, I remember reading a paper about how depressed dipoles in red giants could be either due to mixed mode character or something about the magnetic field. And my question is kind of about like, is there sort of a consensus about how this can be resolved, and the different scenarios could be resolved through astroseismology?
That's a great question. So I'm just going to go back to this plot here where I have the, is this still working? Yeah. Where I'm showing the properties of these waves. So there's something that I glossed over in the interest of time, which is that, remember I told you that that the period of G modes is about equally spaced. But if you look at these modes here, like the L equals 1, you can see that the frequency is about equally spaced. Okay. Now that's what you get when you have sound waves. Okay? These modes actually aren't completely G modes; they're what's called mixed modes, which means that the outer part of the star, they look like sound waves, and in the inner part they turn into gravity waves. Okay? Because of that sound wave character, the frequency spacing is about constant. Okay, so kind of the things that are going on are a little bit complicated because of this mixed sound wave, gravity wave characteristic. So in particular, the prediction of this model with the magnetic fields is that the L equals 1 modes, the red modes, should be depressed. They shouldn't be completely eliminated. And the reason is that when the sound wave propagates inwards, part of the wave gets converted into part of the wave goes into a G mode, which in our picture would then go into a magnetic wave and damped out. But part of it just reflects back as a sound wave. And because of that, the mode gets depressed. It's not completely eliminated. Now, if the amplitude starts off as being kind of small, then maybe it's not detectable anymore. Now, there are still some questions about this model. In particular, I think that some people say that even that if you look at these depressed modes here, that they still have some G mode-like character, which would be inconsistent with the magnetic theory. Because with the magnetic theory, what we're saying is that the only reason why you see anything here is that it's just the sound wave part of the oscillation, which is still remnant, even though the gravity wave part got completely damped up by the magnetic field. Okay, so some people say that there is still a gravity wave component of these waves, which would not be predicted from our theory. Now, there are some models of the interaction of these waves with magnetic fields, which might preserve some of the G mode characteristics. I personally do not think that those models are very convincing. But as far as I know, there's no model for this phenomenon which does not invoke magnetic fields at all.
These little L's, most of the excitation is in the convector zone.
The excitation is all in the convection zone.
So that's pretty robust. I mean, you can't play with the excitation.
That's right. Yes. Yeah. That's right. Yeah. In this case, they're all excited by convection. So yeah. So that kind of simplifies the excitation picture. Oh, that's a good point, Chris.
Okay. All right. So I think we can maybe just adjourn right now. And if anyone has additional questions, we can chat upstairs. But thank you again, Daniel, for a wonderful talk. And we'll all chat upstairs. Thank you.